Hello everyone, and welcome to the first lab of Physics 1. So for this lab, we'll be studying constant velocity, and first off, let's discuss what velocity is. So we know velocity is just speed and direction of an object. So in order for something to have constant velocity, it just needs to be moving in the same direction at a constant speed, with no uh, acceleration or change in motion. And so for this study, I chose to study the motion of a tennis ball, which weighed about 57 grams. And then after recording the tennis ball footage, I tracked its position at specific time frames to get a data of its time and motion. Before moving on, um, I just wanted to discuss what the system and surrounding would be for this experiment. So since we're studying the tennis ball, which will be the system, everything else acting on the system will be considered the surroundings, so any force or anything else. So here's the video. Is moving in the is moving to the left, and so after tracking its position, we get this data right shown to the right, and from this data, at time equals 0 seconds, we get the position vector shown right here down below. And then from this, we can calculate the initial velocity, which is just the final position minus the initial position over the time difference. So for the final position, I just picked at time equals 0.033 seconds, which was this data right here. And then I just took the difference of those position and then over the time, and I was able to get this velocity vector in meters per second. And before moving on, we need to discuss Newton's second law, also known as the momentum principle, which just states that the net force acting on an object is equal to the rate of the change of its momentum. Um, so meaning that the net force acting on the system, which is the tennis ball, is the effect of all of the force exerted on it by its surroundings. In its most basic form, we see it being equal to a derivative of the momentum over delta t. And then if we rearrange it, we get the momentum update formula shown down below. And then if we divide everything by mass, we get the velocity update formula. Now, this is a very crucial formula, which we can use to predict future positions. And the formula is shown right here. And so in order to get our predicted data, we used a coding algorithm to produce the graph shown to the right here. And we just inputted the position vector of initial velocity, um, delta t, and then also the stopping point. So it just ends at the same time the ball was out of the video frame. And then we also give it the force, which is just the zero vector, and then also give it the velocity update formula so it can predict future positions. And here to the right is just a graph of, after we run this program, we get this graph right here, which just moves in the negative downward position. Now, when we compare these two, the observed and the predicted datas, we can see that's pretty much similar until like about halfway where the predicted moves a little bit faster or is shown a little bit more steeper. We can just probably be due to precise timing or rounding errors. But so for the most part, it's just moving in the negative x direction because the ball was moving to the negative. The ball was moving to the left. And now let's discuss, or let's get further understanding for our experiment. So, what if the tennis ball was moving in the positive x direction? What would change? So, first, it'll be moving to the right direction, and then the ball or our graph will be in the first quadrant and moving upwards instead of downwards. And then, if we're asked how many pushes or pulls, we need to get a net force of 0, we could just say that due to all the forces acting on the tennis ball in various directions, they cancel each other out or bounce each other out. So there really isn't a amount we can give. And that will wrap up lab one.